We can also calculate the errors and quantify them for linear regression. If you remember, for the statistics, there was this measure of central tendency, the difference of the data and the mean of data and the square of them. So this was called ST, and we were finding the standard deviation and the variation or variance using this and by dividing this by n-1 in the statistics. Similarly, in least squares, we have a similar formulation. You can see here, this is the straight line formulation, and this is the data. So difference of these and square, it's very similar to this one. The straight line basically means the mean value. Here is the straight line, basically. So it's a measure of central tendency, again, but based on this straight line. So this is given as SR. So we minimize this. So it has to be like as close to 0 as possible. And this similarity of the statistics measure of central tendency and the least squares measure of central tendency can be extended further for cases as follows. Basically, the spread of the data points around the line is of similar magnitude along the entire range. So basically, they all have near zero values. And you can see here a regression line, for instance. And this is the measurement, and this is the point on the regression line, which is a prediction of measurement by the straight line formulation. And the difference between this is basically this. So this is the difference, and we take the square of it and sum them all for each data. So basically, the residual in linear regression represents the vertical distance between a data point and a straight line prediction. This is the vertical distance. So another feature is that the distribution of points about the line is normal. So there will be some distributions of these points. Actually, there is one point here, one here, for instance, and there is a regression line. So distribution, also the errors, will have a normal distribution. And the least squares will give the best or the most likely estimate of A0 and A1. That's why in statistics, because it gives the most likely value, it is called the maximum likelihood principle in statistics. In statistics also, some lines or curves are fitted as a distribution to data, and it's called maximum likelihood principle to minimize this value. If you remember, the standard deviation in the statistics was the spread around the mean. So we have a constant mean value, and the data was spreading around it, and the standard deviation was a measure of the spread around the mean. In the linear regression, the mean is not constant, but it's just the regression line. So basically it's changing. And that's why it's a very similar analogy with statistics, that the standard deviation for least squares is the spread around the regression line. So we have data spreading around the regression line, and the distances, the errors actually, the standard deviation can be a measure of it. Here there is only sy because it's changing on the y-axis because the mean is constant, but here yx because we have change in x and y in both directions. That's why it's just a different demonstration of the same standard deviation, and we are using the least squares formulation here, sum of squares, and n-2 instead of n-1 here. The reason of using n-2 is that for a linear regression we have two data, actually two coefficients that we need to find, A0 and A1. So we divide it by n-2 because two data derived estimates A0, A1 were used to compute SR. Thus we have lost 2 degrees of freedom. Also, if you remember, in the standard deviation for statistics, for one data there was no standard deviation because it's just one data, there is no spread. That's why we wanted to have the standard deviation like indefinite. And if we set n-1, this becomes 1 and 0. So division by 0 is like not a definitive it is not, you know, defined as a number. That's why we can have the same analogy for here. We have only, so we have two coefficients, two unknowns, and especially for 2 points, let's say. The spread of data around a line with 2 points, there is no actually a spread for 2 points. Let's say we try to have a line between 2 points. It's just straight line that pass through these. That's why there is no error. So there is no standard deviation. To achieve that, we also want to have an indefinite and not defined standard deviation. We simply subtract 2, and if n is 2, this becomes like not defined, similar to the statistics. That's why we use n minus 2 here. These are the two reasons. Okay, we define a least squares regression to the data, and we can also have a measure of this goodness of fit by using this residual error metric. Before the regression, we actually have the statistical information, the difference of the data from the mean, the total sum of the squares around the mean for dependency variable. So this, we already have this. After the regression, we can have the errors as a difference of the data from the regression line data or prediction. So sum of squares of the around the regression line. And the difference between after and before these metrics, ST minus SR, quantifies the improvement or error reduction due to describing the data in terms of a straight line rather than its average value. So because the magnitude of this quantity is scale dependent, the difference is normalized to ST. So we have ST minus SR divided by ST. ST is the before regression value. So this kind of a error metric. So it is defined as R square, which is called coefficient of determination. Also, we can take the root square of it to be able to convert it to the same unit of the data, and it becomes R correlation coefficient. This is very commonly used, and this, so by implementing the formulation of these, basically R is calculated using this formulation. And you can see that we are using the same summations of the data information that we use to find A0 and A1 in the least square to calculate the correlation coefficient as well. So if R and R square is 1, it's a perfect fit, which means SR is 0. So we minimized it and we have a perfect fit. And it signifies that the line explains 100% of the variability of the data. So that means a line fit is suitable for this data. So, but if R is 0, then it is the worst fit. SR is S2, so there is no fit actually. And that means the fit represents no improvement from here to here, before to after. There is no improvement to be able to get a fit. That means the line is not suitable to have a fit for this data. So this means that if we get closer to 1 when we calculate R or R square, close values to 1 means that we have a good fit, or the line regression, linear regression, is good for that data. We can use it for that data.